Okay, we're talking about Young's double slit experiment today. And first of all, we talked about this idea that when a wave is coming towards, when a big plane wave, in other words, a big wide wave comes and hits an open spot like this, it creates these wide waves. But the smaller that this opening becomes, the more rounded the wave becomes, so that it looks like the wave is coming from a single point source. But if you have two of these next to each other, these two waves are going to start to overlap. It'll start to look like this. Actually, let's do a... I think I like this one really well here. That obviously isn't working. Let's try this one. Looks like nothing's working today. Goodness. All right, I'm going to look it up on Fet.Colorado. It'll definitely be here. Let's see here if we can find the right one. Oh goodness, you gotta be kidding me. It should be here somewhere. Here we go. We'll use this one. So if you have water waves, you have a single point source that comes from dropping this water into this drop of water into the water, and these waves propagate outward, right? And if we put two drips in there, then the waves can overlap each other. They can build up on top of each other and overlap. These two drips are not happening exactly at the same time. And so if we put them, maybe they are happening at the same time. So anyway, if we put these further apart, you can see that as the waves overlap, we get bright spots, which are the big waves, and then dark spots, which are the low waves, high waves and low waves. And it changes as you move them further apart. But another thing that's kind of interesting is that if you create put a little wall here, and these waves come out, you create new waves out here. So that's kind of interesting. And if you have two of those barriers, you can actually create waves out here as well. So lots of different things that you can do. You can do this also with sound. You can have two sound sources, and you can create dark spots and light spots. The dark spots are where the sound cancels out. The light spots are where the sound is very, very strong. And you can space these speakers further apart and see different patterns of dark and light or loud and soft. But light is also a wave, and you can do this with light. So with light, if we have two lights going on here, you can see that the light waves overlap. And if we had a screen out here like this, we would get light spots and dark spots, right? You can also do it with a single light and just put a barrier in there that has two holes in it. And you can create a similar effect with this light out here at the screen. Let me see if I can get it to work properly. Nope. So when you have these two holes in the wall, you create two waves on either side from one wave, and then you get the light to dark, light, dark, light, dark over here on this screen over here. And this is what we call interference. The two waves interfere with each other, overlap each other, and create high intensity parts and low intensity parts. And this is always what happens with waves. It happens with water waves, it happens with sound waves, and it happens with light waves. And this is how Thomas Young detected or determined that light was actually a wave, a type of a wave. And this is the beginning of studying light as a wave. Oh, we should do one other thing here. Another interesting thing that changes, over here you can see that we've got 3 bright spots and 2 dark spots, but we can also change that by changing the frequency of the light. If I change it to green, for example, the frequency changes the wavelength, and it will actually change the number of spots that we have out here. If we go higher in frequency and shorter in wavelength, let's go all the way out to the blue or the purple here, see what we get. Here we've only got 2 bright spots and 1 dark spot in between, and these little dark spots out on the edge. Go out to purple, see what happens. In the purple, we only have these 2 very, very, very hard to see dark spots or bright spots out there with 1 big dark spot in the middle. If we go with the deeper red, we actually end up with 3 again, not as easy to see, but it changes it. If we change the amplitude, we just change the brightness of these things. But changing the wavelength actually changes how far apart these spots are, or these bright and dark spots on this screen. You can also change that by changing where the screen is relative to the light and the slits. So there's lots of things that change as you change the properties of the light. What's going on? Why is my mouse misbehaving? Ah! My computer is misbehaving in general here. I think we just had an internet reset here. Still not sure what's going on with this mouse, but something is going on with it. Something goofy. All right. Okay, so back to this diffraction here. So, one of the things that was figured out as they started doing more and more experiments like this is, of course, a formula that determines or that describes and predicts where these light and dark spots will be. And essentially they came up with two equations. One equation that shows, how come I can't move anything now? Good night. There we go. One equation which shows where the bright spots will be for any particular wavelength of light, lambda. If you have a distance between the two openings where the light comes through, d. Let's see, is that right? The d is actually the difference between the two paths that the light will take. That's the distance difference between the two paths. I thought that didn't look quite right. So what's going on here is that we have two different, and that actually happens to be equal to d if you have a small angle formula. But essentially you have these two very, very small openings that the light comes through, and this comes from the same light source. And this light travels along these two different paths to get to this single point up here, some point on the screen up here. And for that change in that distance, that difference in distance, it ends up equaling d, which is the distance between the two openings, times the sine of the angle, which is the angle, the elevation angle essentially. But that angle tends to be a very small angle when your screen is very far away from your light source. And if you have the sine of a very small angle, it ends up just equaling, this ends up just equaling 1. And then your delta L, it just ends up equaling the distance between the two holes here. So that's why it ends up equaling that number. So then you can use that to determine where all the bright lights are going to be. Well, how do you determine it using this equation that has this m in it? Well, the m is the order of the bright spot, or the order of the interference. The one that's right in the middle of this thing, which is the brightest one, is going to be order 1. I believe they give it. No, they give it order 0. So this one right here in the middle is order 0. And then this first one is order 1, and then the second one's order 2. So that would be where your m is. M equals 1, 2, 3, or 0. And then you can calculate where it's going to be. Of course, for order 0, it's going to be at this 0 spot. It's 0 angle from the center. And then all the other ones are going to be at different angles upward. M times theta, difference in distance. So if your wavelength is 500 nanometers, for example, then you would have 500 in your lambda here. And if you wanted to know where this one is going to show up, you would have 500 times 1 on this side of the equation. Now on the other side of the equation, you're going to have the distance between the two holes where the light's coming out times the sine of the angle between your thing here, your middle point here, and the point where you're actually trying to measure that. So here's how you use the equation. And of course, there's a different equation for the dark spots. We usually measure the light spots, but that's okay. So we're using a helium neon laser, which has a particular wavelength. The particular wavelength of a helium neon laser is the thing that we're actually trying to measure. We actually want to measure lambda. So we have these two slits that are separated by 0.01 millimeters, and it has to be pretty small. It has to be almost as small as the wavelength of the light. So 0.01 millimeters is close to that. And then we want to find the third bright line, which would be the m equals 3. Actually, the m equals 3 would be the third one, not counting the center one. And it turns out that it's formed at an angle of 10.95. That's something you can just measure using some geometric tools. And we want to know what is the wavelength of this light. The third bright line, it turns out, is the m equals 3, of course, and it's the distance between the slits is 0.01 millimeters. We need to convert that into meters. And then the angle of 10.95. We plug all these things in the correct way. We can actually leave it as millimeters if we want to measure our wavelength in millimeters, and that's fine too. But if we turn it into meters, it'll probably make a little more sense. But we plug all these numbers in and solve for lambda, and we get 6.33 times 10 to the minus 4 millimeters, which would happen to be 6.33 times 10 to the minus 7 meters, right? Which happens to be 633 nanometers. So 633 nanometers is our wavelength of our light for helium neon laser, and that is correct. It is a red light for helium neon lasers. So we want to know what is the highest order possible, or how many different dots can we observe if we're looking at a laser like this. Well, essentially, you can observe everything out to a certain angle, right? Once you get to a certain angle, 90 degrees in particular, then you can't see anything, because if you go out 90 degrees, you're looking sideways, right? So if we're looking on a flat screen, we can only see things out to 90 degrees, and what we do to calculate this is we plug in the sine of 90 degrees, which ends up being 1, and then we plug in the size of the distance between our two holes where our light comes out, and we also plug in our wavelength. And it turns out we can get 15.8, or we can get 15 orders of bright light, or they call them fringes. But sometimes we get strange patterns like this, where instead of just going from bright out to very, very dim out at the end, you also get some variation in between. We get bright and then dark and then bright and then dark here. And that's actually interference that comes from just going through the single hole. So you get lots of different types of interference going on with waves. It can be very interesting. But another very interesting thing that you can get from these diffraction patterns is the things that you can get from white light, because of course white light is made up of all different colors of the rainbow. And since every one of those colors diffracts at a different angle, you get rainbow diffraction. You essentially get little rainbows going everywhere. And that's exactly what you guys discovered when you saw diffraction through the prism and everything else in your experiments that you did last week. Well, here are some interesting things that happen in nature. This is an opal, an Australian opal. And the color that you see in the Australian opal is because of diffraction. It's not because of the color of the rock, it's because of diffraction. You actually see these colors bouncing off of and bouncing through the crystals and create this diffraction and splits the white light into many colors of light. This is also why you see colors on butterfly wings. Butterflies' wings are not particular colors. They don't have pigment. If you could actually see their actual color, quote unquote, it would be grayish whitish color. But what happens is there are little ridges and little kind of reflective bumps on the wings of butterflies that diffract different wavelengths at different angles. and you get diffraction patterns. They interfere with each other, and you get light parts and dark parts. And the dark parts of the butterfly wings are not actually dark colors on the wing. They're actually just places where the waves interfere with each other and cancel each other out. And the bright spots are not bright colors on the wings. They're actually just places where the light has interfered with itself and created a constructive interference. This is also true of many bird feathers. Many bird feathers create their colors like hummingbirds. Hummingbird feathers create their colors this way as well. So with white light, when you do a diffraction, when you make a diffraction pattern with white light, you often get rainbows instead of just single lights. And with that, you can get a spread. You get a spread of colors, or a band of colors, and then a band of dark, and then a band of colors, and a band of dark. But it still obeys the same rules. You just have to calculate each end of the band using a different wavelength. So at the purple end of the band, you have to use purple wavelengths, and at the red end of the band, you need to use red wavelengths. And they do that here, calculating those angles at different frequencies. Calculate how wide the band is. I'm not going to go into that in great detail. So, what is happening when you just have one hole that the light goes through? You would think that you would just get a single light on this screen over here. The light comes from the left, goes through this hole, it just makes a light and some shadow. That's not what happens. What happens is you get a bright light in the middle, and you get some dimmer, but definitely lights that are there on the side. And let's show you that really quick. I have a single, very small hole that I can shine my laser through with. So this is a very, very small cut with a razor blade probably or something that I can shine this through, this green light through. And you can't really see it very well unless I turn off the lights. So let's turn off the lights. And let's turn off the screen. And let's turn on the camera so maybe we can see it with my computer screen here. All right. So now, if we go further away, we should be able to see it a little bit better. See that bright line in the middle and then the little lights on the side? You can kind of see the dark lines in between. See that? That's what happens, and that's just going through a single hole on this card here that I've got. It's going through like a single door, and you would expect you to see a single light, but you don't. You see many lights. I don't know if that showed up on the screen or not. I hope it did. I should that's what I should do that again. It shows up on your screen, right? So if I shine through there you go. Hopefully you can see that. If I go through 2, it becomes a little more prominent. A little easier to see that pattern. If I go through 1, it's still there though. It's just a little harder to see. Anyway, so that pattern is definitely there, that diffraction pattern, or that interference pattern. And what's happening with that is actually completely due to the wave nature of light. As the light comes through this little hole, the wave essentially kind of bends itself around the corners. You could think of it as. So you can think of this wave as having several wave fronts coming through, kind of like the rays we used in the last chapter. And as they come through, they bend around the corner. Let's see if I can see a good picture of that, show a good picture of that. Oops. I don't have a great picture of it, dang it. Today is going to be a bad day for using the mouse, I can tell. But you can think of each wave that comes through as a whole bunch of different waves. And as they come through a small spot, you have a bunch of different waves that are all coming through, and then they all start to interfere with each other. And as they all start to interfere with each other, then they can make this pattern that has this very bright spot in the middle, but it does have some bright spots and some dark spots to either side. And it turns out to be the same equation, except instead of the d being the distance between two holes that the light's coming through, the d is just the width of that one hole that the light came through. And the other difference is that instead of having m equals 0 in the problem here, which is that one right in the middle, we just use m equals 1, negative 1, 2, negative 2 for this equation. And so you can, for example, you can use a laser to calculate the size of a hole. If you shine a laser through a hole and then let that laser beam hit a screen, and you can measure, and you start measuring the angles that it makes from one bright spot to the next bright spot, then you can use this equation to calculate the width of the hole. And lasers are used to measure the size of things all the time using this equation. That's exactly what they do here in this example. They measure they know the wavelength of the laser, and they measure the angles, and then for the first light they use m equals 1, for the second bright dot they use m equals 2, for the third one they use m equals 3, and so on. And they can actually calculate the width of the hole that the laser went through. Very useful feature. You can use a laser as a measuring device for very small things. Can't remember how many sections we have. Need to check that really quick. Okay. So if you're going to use light to measure small things, and to measure anything really, you need to know how small of a thing you can measure and still be measuring something usefully. And that actually has to do with the wavelength of the light. The wavelength is going to overlap with itself to create these dark and light spots. And if the wave is a certain size, then it's ideal for measuring things of a certain size. But if it's much bigger than something, if the wave is much bigger than the thing you're measuring, it's not going to be so good. And so this guy, Rayleigh, very famous physicist, came up with this Rayleigh criterion, which would show you essentially your the limits of your resolution, or how well you'd be able to measure something using a certain wavelength. And anyway, this is the equation for the Rayleigh for the Rayleigh criterion. You have this angle theta that is the angle between the center point of your light diffraction and the first bright spot of diffraction. And it turns out that this 1.22 plays a role, this Rayleigh constant here. The wavelength plays a role. And then the D here, which is the distance between I believe it's the distance between the size of the object, essentially, the two ends, the distance between the two ends of the object that you're trying to measure, I believe is D in this particular equation. I'm trying to figure that out really quick. Can't remember if that's exactly it, but I think that is what it is. Yeah. Oh, so, no, sorry. The D is the diameter of the aperture, lens, or mirror. Yeah, so the D is the lens of the, it's essentially the hole that the light goes through. So if you're using a camera, it can be a lens or an aperture or a mirror. But if you're using just diffraction tools, then it's just the opening, the size of the opening, the diameter of the opening. Excuse me. So, for example, the Hubble Space Telescope, you can use this equation with the Hubble Space Telescope to calculate the smallest angle between two things that you can measure out there in space. So the angle is important for telescopes, and you use the 1.22 times wavelength over D, and the wavelength that we're going to talk about is going to be in the red range, 550. No, 550 is not red. That's more like yellow. I don't know, whatever it is. But anyway, you've got 550 nanometer wavelength here, 550 times 10 to the minus 9. And then they divide that by the size of the Hubble Space Telescope's mirror, which happens to be 2.4 meters. It's a little over 10 feet. About 10 feet, actually. Anyway, you multiply all this together and you get 2.87 times 10 to the minus 7 radians, which is a pretty small angle. And that's good because the Hubble Space Telescope was designed to look at something very, 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 very far away from it. And the angle that it's going to look at is very, very small. If you calculate the distance for that angle, the distance away that you can see something at that angle, it turns out to be 0.56 light years away. What's that? That's correct. So actually it's not 0.56 light years away, it's a 0.56 light years distance apart. So something that is at 2 million light years away, 2 times 10 to the 6 light years, the Hubble Space Telescope can measure things, or it can see things, you could think of it, that are less than a half a light year in size. So less than a half a light year is like a part of a galaxy. So what this is saying is that if the Hubble Space Telescope looks at something that's 2 million light years away, it can see galaxies in pretty good detail. Okay? Well, that's exactly what it sees when we point the Hubble Space Telescope out there. So let's look at some Hubble images. Here is a Hubble Deep Field image. This is what they saw when they pointed the Hubble Space Telescope into space where they'd never seen anything before. This is just blank parts of space. And each one of these dots on the screen you're seeing is actually a galaxy. And you can see that the Hubble Space Telescope can actually see different parts of each galaxy. You can actually see shape and form in the galaxies.
And this is obviously after they fixed the lens.
I'm sorry?
These are some of the newer photos after they fixed the lens.
So they launched the Space Telescope in 1990, and the first images that started coming back were really blurry. In fact, they were you couldn't even tell what they were pictures of. So they had to fix it because it turns out that they ground the mirror wrong. So they gave it a pair of glasses essentially. And then they were able to take really good images, and these are the very good images, yes. This is essentially, they pointed the Hubble Space Telescope into a part of space where they'd never seen anything before, where they just had never detected any kind of light. And this is what they saw, is just thousands and thousands, even millions of galaxies out beyond our galaxy. But each one of these is several light years across. Like each one of these galaxies is probably a couple light years, or maybe even several hundred or 1,000 light years across. And so the Hubble Space Telescope could see, and this is much further than 2 million light years. This is like 1 billion or more light years out there. This is way out there. So you're seeing, what you're seeing is Hubble Space Telescope's angle of resolution that it can achieve. Here's another telescope, 350 meter Arecibo telescope in Puerto Rico. And it's a huge telescope and has a much, much bigger diameter. But the wavelength that it's detecting is a radar wavelength or a radio wavelength. And so the lambda in the equation is much different for the Arecibo. And so it actually has a much lower resolution than Hubble. Because Hubble looks at the visible light, which is a much shorter wavelength, it can have much higher resolution. But there are telescopes like the Chandra telescope that actually look at X-ray and ultraviolet light. And so it can be a much smaller telescope and have much higher resolution looking at ultraviolet and X-rays. Chandra telescope is very good at looking at things very far away. Excuse me. If you want to know the resolving power of a telescope in actual size rather than angle, then you have to also know the distance. And that's, I believe, what they're doing here. Yeah. So the D is still the aperture. But little d now is the distance between the specimen and the objective lens. So they're looking at something very, very far away, and if you know that distance, then you can actually calculate what your magnification power is in size. But you almost never know that distance really, and so it starts to get a little bit confusing, and those distances get really big. But this is very useful for microscopes, which you can easily measure the distance. So for a microscope, you can get the resolving power as a ratio rather than a angle, and that ratio ends up being the resolving power. So it's like a 500 times or a 200 times microscope or whatever. And of course, you guys got some experience with that, hopefully, when you built your microscopes and your telescopes. But those things come from the wave nature of light. I'm going to leave thin films. Let's see. No, I think we'll finish up here. We'll do thin film interference and polarization today. So soap bubbles create what's called thin film interference, and so do glasses that have anti-reflective coating and other things that create that little rainbow effect on them. And this is how it works. It's really quite simple once you blow it up and kind of see what's going on a microscopic or a nanoscopic level. But some materials are very, very thin but see-through. Like soap bubbles. Soap bubbles are extremely thin. Their thickness is close to the wavelength of light. And as light comes into them and diffracts or refracts into the soap bubble, it turns as it goes in the soap bubble. But on the backside of the soap bubble, it also bounces back a little bit. And as it bounces back a little bit and comes back out the soap bubble, it comes out almost at the same time as the original reflection off the front edge of the soap bubble. And these two lights come out so close to each other because of the thinness of this soap bubble, because the bubble is so thin with soap. They come out very close to each other, so they almost come out on top of each other, so they can interfere with each other. The waves will overlap, in other words. And these overlapping waves create interference. They create a light spot, dark spot, light spot, dark spot. And the equation, again, is very similar to the equation for the two-slit experiment or the single one. In this case, you do have wavelength, but instead of distance, you have a thickness of the film, which is T. And you also multiply by 2 times the thickness because the wave goes down through it and then bounces and goes up through it again. So it goes through it twice. And you can actually start to measure things. You can measure the thickness of the film, for example, and that's what they're doing in this case. In this case, they're shining a known wavelength of light through this material, and they're calculating the thickness of the material by the distance between the light and dark spots that created in the diffraction pattern. But you also have to know how the wavelength changes when it goes into the soap bubble, because it will change. And that has to be done by dividing the original wavelength by the what's the word for that? They have it right here somewhere. You have to divide it by the I can't remember what that's called. Index of refraction. Thank you. Index of refraction. You have to divide your wavelength, your original wavelength, before the light hits the soap bubble, by the index of refraction of the soap bubble, which is n, right? So it comes in through air, for example, and then it hits the soap bubble and it goes through the soap bubble for a very short path, but you still have to divide that wavelength by that index of refraction of the soap bubble to calculate the thickness. And then you calculate the thickness using this equation, 2t equals lambda sub n over 2. And you can get the thickness, which in this case turns out to be 99.6 nanometers. It actually is much shorter than the wavelength of the light, much smaller than the wavelength of the light.
So why is it being used?
What do you mean, 2 equations?
Well, one of them we're taking our wavelength and dividing it by index of refraction. Another one.
You're doing it in both. This one is the lambda sub n with the n on that is equal to this. Lambda sub n is equal to lambda divided by n. So they're just making a substitution. In the next example, they use the same equation, but with different thicknesses. So, for example, if you have constructed, so this one is a thicker. It's a 650 nanometer. No, sorry. This one is a 610 nanometer thickness, a 360 nanometer thickness, and 120 nanometer thickness. So they do it for 3 different thicknesses because they get 3 different orders of destructive interference. So they get where it's lambda times 1, lambda times 3, lambda times 5, and it turns out that it is those odd number orders that you get the different constructive interferences, and then you get different thicknesses of the soap bubble. And that happens with soap bubbles. At the top of the soap bubble, for example, it's the thinnest because gravity is pulling the soap down towards the sides. And the sides of the soap bubble, the sides of the soap bubble are thicker. Also, different angles through the soap bubble can make it thicker, but not such a big deal. You can see this effect when you put two pieces of glass together and you separate them with a very, very thin piece of material like a piece of paper, you can also see this effect. Sometimes you see this in multiple panes of glass that are just laid together, just because little pieces of dust separate the glass by little amounts. So if you put two pieces of glass together, you can often see this effect a lot. Here they also show this effect just by putting two lenses together. Just because the lenses are bent, you put them together, they create this effect because the path length is different because of the bent glass. This is what we call Newton's rings. Newton was the first to observe this. So lots of different interference effects happen in different situations. One of the more interesting ones that we don't really think is attributed to the wave nature of light necessarily all the time is the idea of the polarization of light. So here are two different pictures of the bottom of a river. The one on the left just uses a regular lens, and you see lots of reflection, clouds, the sky, and other things. This one on the right is taken with what's called a Polaroid filter, and you see no reflections, hardly at all. Why do the reflections go away? Well, again, this is because of the wave nature of light. Remember that light is a wave of electrical and magnetic energy, or electrical and magnetic fields. You have this electrical field that's going one way and the magnetic field that's going the other way. Now, most light out there is not just electrical field going one way all the time. Usually it's changing, it's rotating. It's what we call elliptically or circularly polarized, so that the electric field is rotating while it's moving along, so the electric field at any given time and place is in a different direction, and the magnetic field is perpendicular to it. However, when light hits a horizontal surface, it changes it. So let's explore this idea of polarization, first talking about ropes. So let's put a wave on a rope like this, up and down, and we put it through an opening that is also up and down, and the wave will survive because it will be able to go through that opening. The wave will be able to wave up and down through that opening and make it through. If we try to put through a sideways wave through an up and down opening, then the wave will actually hit the sides of this door and it will stop the wave. We can do a similar thing with light that is polarized in all kinds of different directions. So here, this shows a wave that is coming towards us out of the page, and it shows that the electric field is pointing in different directions at all different times. So in other words, this wave is random polarization. It's got all kinds of different waves going in all kinds of different directions, all kinds of different sources of wave. So the electric field is just pointing everywhere. There's electric fields everywhere. But we can put it through a filter that's only going to allow a certain wavelength of light through. There are different ways to do this, but one way to do it is to put it through a piece of glass that has metal on it that will reflect all the waves that are going in one direction and let through the waves that are going through in another direction. So this kind of filter will reflect all the light that's going that's going side to side, but it will allow through all the light that is going up and down. Okay? So this filter is only allowing through certain wavelengths of light that are going up and down. And you can actually put two of these together and rotate one of them 90 degrees so that you're letting through none of the light when you rotate them through. So that one is letting through the light that's going up and down, the other one's letting through light that's going side to side. And when you rotate them together, They don't let any light through. And let me show you what that looks like. Grab that polarizer here. Okay, so these are both polarizing filters. This one is designed to let light through at different, it's actually polarizing different colors of light. And the reason you get different colors is because the projector has different colors of light coming out and they're polarized in different directions. So if I hold this up here, that's half of the light through, but it only allows certain colors of light to come through. Obviously, it's letting purple light to come through or red light to come through when I hold it this direction. If I turn it 90 degrees, and if I turn it 45 degrees, it just allows all light to come through, but it's kind of grays out the picture. So it's only allowing half of the light to come through. If I turn it this way, it allows all the green light to come through and blocks the purple light, or blocks the red light. And the same with this one. This one is selecting different colors because the colors coming out of the projector are polarized in different directions. But if I put it at this angle right here, I get gray light. And this one here, I also get gray light. And if I put them over each other, I get nothing. Because this one's blocking out half the light, this one's blocking out half the light. However, if I turn this one over to this side, so it's gray, and this one is still gray, actually right there, I can actually get gray again, but it's blocking out more light, more than just one. And if I turn it just right, I should be able to get a block out about the same amount of light. But as I rotate them, one of them will stop blocking. This one's blocking out electric fields going in one certain direction, maybe up and down. And maybe this one's also up and down. But if I put them together and I start to rotate them, so that this one starts to block out ones that are at 90 degrees to the other one, they'll block out all of the light together. So this one's blocking out up and down, this blocking out side to side, and between the two of them, they block out everything. Because anything that's at an angle between up and down and side to side is partially up and down and partially side to side, right? So what's this got to do with reflections off of water? Well, it turns out, and here they give us an equation for, the equation is essentially just a cosine squared of the angle. So you can calculate the intensity that's blocked out by a polarizing filter using that equation. It's not very difficult. Just have to know the angle and the original intensity. But why does this have anything to do with water? Well, here is unpolarized light coming into water. Unpolarized light shining down on water. But because water is a horizontal surface, it only reflects horizontally polarized light. All the stuff that's vertical doesn't get reflected toward your eyes. Okay? Only the horizontal stuff gets reflected. The vertical stuff essentially disappears. It doesn't disappear. It actually goes down into the water. But anyway, the horizontally polarized stuff, the stuff that is horizontal across your plane of vision as it's coming towards you, is the stuff that you end up seeing. So you end up seeing polarized light that is polarized horizontal to the plane of the water as you're looking at it. So if you want to block all that reflected light that's coming down from the sky and bouncing off the water, all you need is one of these polarizing filters that is turned in just the right way so that it's blocking everything that's horizontal. And if it's turned just the right way so it's blocking everything horizontal, what you see is just what's at the bottom of the pool instead of reflections off the top of the pool. This is why drivers wear specially made glasses. They're polarized glasses that they wear. And they don't look like normal sunglasses. They look like sunglasses that have just a slight tint to them because they're polarizing filters. And they polarize reflections off of the road because you can get reflections off of road too, especially when it's wet. Also, people who drive boats, they wear polarized glasses all the time. It will prevent reflections off of any horizontal surface, off of the hoods of cars. It will put off of the streets, off of reflectors, off of the streets, everything. It will block all those reflections and make it easier to see things. It will not block reflections off of vertical things, like a vertical surface. Reflections off of a vertical surface will not be blocked by polarized glasses because the polarized glasses would have to be turned sideways. You'd have to turn your head sideways to block that. And if you turn your head sideways with polarized glasses on, it causes a weird effect. You will start to see reflections. So if you wear polarized glasses at any time in your life, turn your head sideways and see what happens. Here they show how this works. You have these, usually what they do is they take these polymers, like plastics, that have these conductive molecules in them, and they stretch them in one direction to create these little lines in the material. And those lines are essentially like they're like the holes that allow things through or don't allow things through. So the electric field that's going to come through this, that's going to go through this, is actually going to be perpendicular to these molecules. The ones that are parallel to these molecules is going to get absorbed by this conductive quality. So the electric field is going to go back and forth with those molecules and dissipate that field. So it's kind of interesting. It's actually opposite to what we showed with the ropes, but it's still what's going on there. Here's an interesting polarizer that I actually have that very few people will ever have because I used to work for the company that makes these. These are quite expensive. With this particular polarizer, instead of just blocking the light, it actually reflects the light. So here's one of the polarizing filters. Here, there's another one, both purple, green, so they're still polarizing light in different colors because the light has different polarizations there. As we bring them together, you can see that they're almost perfectly the same when you line them up like this. Like here's one of them, here's two of them, it makes no difference, does it? Like having two is the same exact as having one. These are extremely high quality filters. That means they still let through the same light no matter how many filters you have there. However, when you start rotating them, you do get that blocking out effect. But if you'll notice, it's not just blocking it, it turns into a mirror on this side. You see that? See that it's a mirror on this side? So it actually blocks it completely and reflects it back towards the source. These are what are called thin wire filters. So what they do is they take a piece of glass and they coat it with silver or aluminum or something like that, some reflective metal. And then they use beams of electrons, I think it's beams of electrons they use. No, I think it's beams of atoms. But anyway, they use some beams of particles to cut off these, to cut off the metal that they put on to etch it. And they actually use beams of particles combined with an acid, hydrofluoric acid, which is a very dangerous acid. Like a drop of pure hydrofluoric acid will dissolve all the calcium in your body and kill you, like very quickly. It's very dangerous stuff to have around. But that's what they use to do this. So it's very interesting. These thin wire filters, thin film filters, anyway. Got those from the company I used to work for. Anyway, interesting stuff, these polarizing filters. So let's see here. Here they use reflection, the reflection law, to talk about how light reflects off of water compared to how it goes into water using Snell's law. So you can use total internal reflection and Snell's law to figure these things out. Actually, they're using this is Brewster's law for internal reflection, which is what they're using. If here, which we did use before. And this one can tell you the angle, the maximum angle at which you can reflect light with this polarization, and they use that down here. Excuse me, they calculate it for different materials. The first material turns out to be water, 1.33 they're using. So you're going from air to water, 1.33 on top, air, which is 1 on the bottom. And then for crown glass, it's different. Crown glass is 1.52 for its index of reflection, divide that by 1, and that's equal to the tangent theta. And that gives you that angle of reflection, which they call Brewster's angle. They show another one here, another way to polarize light. So when light is coming in from the sun, for example, it can actually hit molecules and come straight down and become polarized. And in that case, it becomes polarized side to side again, kind of similar to water. There's lots of ways to polarize light. You can do it with crystals. And this is actually what's going on in the projector up here, is they have different lights that are polarized in different directions because of the liquid crystals that they go through. And you can create different effects on the screen, different colors, different other things. So used a lot with screens. You can also create polarization by putting stress on an object. So this is a piece of plastic that's been put between the jaws of pliers, and then they squeeze it. And as they squeeze it, they create polarization in the light. And so you can actually study materials. You can study how materials are reacting to pressure by looking at the polarized light coming out of them. And that becomes quite interesting stuff too. Excuse me. And that takes us to the end of the chapter. And they talk about enhanced spectroscopy, microscopy rather. We'll talk about this later actually, because it's more interesting when you talk about it during atomic physics. But anyway, let's talk about now what's going to go on for the rest of this week. Tomorrow, I will not be here on campus. I will be in McCook, going to enter High Day, and so we will not have a lab tomorrow. However, we will meet on Thursday and have our lab on Thursday, at which time we will finish up whatever you haven't finished up for the eyeball tank lab, and then hopefully have time to do some experiments with wave optics. So we will meet on Thursday at our normal time and do a lab on Thursday instead of a lab on Wednesday. There will be homework for this chapter. You can see that it's not terribly difficult. It's just a couple of equations with sines and cosines and tangent and whatever. It's not terribly difficult stuff, but we will have some homework from this chapter. We did not have any homework from the eyeball tank chapter. I don't think I posted it, did I? From the eyeball chapter. Did I put two problems on it or something? Two. Okay. Okay. Well, there should be 2 homework assignments. I'm just not sure. So we should have one that's about geometric optics, and then vision and optical instruments. Did I have anything in there?
We had 24 and 25.
24 and 25. Okay, 26 I'm not doing a homework assignment for. I think that the lab is better than the homework, so I'm not going to do the homework. But we will have something for 27. Won't be huge, but we will have something there. And then we will get on, then we're going to move on to what we call modern physics, 20th century. Woohoo! So we're moving on to the 20th century in chapter 28. And then from here on out, it's just 20th century stuff. We're going to leave behind everything that we've done and move on to the past century.
So, I remember you mentioned the math with the colors. Is that coming up soon?
Yes, we'll see that in particle physics here.
Oh,
We'll see a little bit of it here in nuclear physics, but mostly particle physics.
It's kind of interesting to see how that kind of works.
This also means that we need to have a test here probably next week. Is that what you're going to ask? Because this is the end of our next section. So how many tests have we had so far? Just one. The first one covered covered everything all the way through from 18, there we go, through 21.
21, 22.
I think it was 21. This one is going to cover 22 through 27. So it'll cover circuits, no, it'll cover magnetism, electromagnetism, and optics. And then the next test will be the final.
Well, do you think we have a chance to look at these assignments for 24 and 25, and the ones that we're having problems
So we've got time right now? Sure.
So the next exams are running 22 through
22 through 27. So the next exam will be next week after we're done with 27 this week, with our lab this week.
I mean, in 2 weeks?
Next week is spring break, right? What I'll do is I'll open up the exam this week in case you want to take it before spring break, because you definitely, taking a week off can be a bad thing. So I'll open up this week if you want to take it this week, but if you want to take a week off and study more and do all that, you can take it the week after spring break as well. And then after spring break, we'll come back and it'll be 20th century physics for the rest of the 20th and 21st century physics for the rest of the semester. Which is really kind of good because the 20th and 21st century physics is so beyond us mathematically, for the most part, that we won't really have a lot of math to do. For special relativity, we'll have some. For quantum physics and atomic physics, we'll have some, but not much. There's not a lot of problems that we can do in this class, so it's pretty straightforward stuff. Not all that challenging. It'll be a relief.
Go over 24 questions for problem number 4.
Yes. Let me just put this away really quick. Excuse me. Okay, so 24. Let's see, let's go to the proper. Number 4.
Number 4 and number 5.
Are these ones still open?
No, I think
Let me fix that too, I suppose. Okay, so here we have a radar is detecting the presence of aircraft. It's reflected off an object 5.5 times 10 to the 5th minus 5 seconds after it was transmitted, right? They want to know the distance.
I don't think that's right.
What?
That's not it.
Oh, which one?
Chapter 25, question.
Oh, chapter 25.
Question 4. And it's the one with the diagram.
5, chapter 4.
Oh, yeah, that was.
Chapter 25, number 4.
Yeah, that one.
Ah, okay. So, dive in a pool and extracting on the edge. Indices of refraction air and water different. Light rays coming, changing, appearing. Diver sees the instructor at an apparent angle of 27 degrees, measure normal to the interface. So that's the angle down here, right? The diver sees the instructor at this angle here. So the most likely mistake that students will make with this one is to get the angle mixed up with the index of refraction. This angle that the diver is seeing here is actually the one that's going to go on the same side as the index of refraction of water. Okay, so in your equation, it looks like this.
The Snell's law.
Yeah, let me look at me. So the way that they've done this is a little bit confusing. What they've done is they've got the diver down here, and they've got the diving instructor up here, and they've shown the angle that the diver that is associated with the diver. They've shown it up here with this dotted line. Right? It's actually this angle down here. This is your theta A. Is this angle down here. So when you use Snell's law that says N1 sine theta 1 equals N2 sine theta 2, you're going to have an NA sine theta A, right? Replacing one of these 1s or 2s or whatever. So this, let's say that this is the N of water and the sine of the angle in the water. That's this angle down here that they gave you. And the N2 is, of course, 1 for the instructor. And the sine theta 2 is the thing you're solving for. My guess is that you switched the angle theta A with the angle theta 1, with the angle theta for the instructor. But this should be the angle they give you. So you should have the N of the water, which is like 1.3 or something like that, times the sine of the angle that they give you, whatever that is, sine of the angle that's given, equals 1 times the sine of the angle you're trying to figure out. And then you solve this equation. Does that make sense?
It's asking for the height of the
Once you've solved for the sine of the angle, then you can use geometry to solve for the height of the instructor. So let's go back to our problem. Once we have the angle that the instructor sees at, then this is just a triangle with a 2 meter long base and an angle here, right? Then you can use the tangent, because the tangent of this angle will equal the height of the instructor over 2 meters, right?
I use the sine.
Can't use the sine unless you know the hypotenuse, right? So you have to use the tangent. Does that make sense now?
I think I was a little confused about how I portray that in the picture. So that we'll be using the index of refraction of water with the
Times the sine of angle A.
the sine of the angle given. Okay.
And then that equals the sine of the angle for this, for the instructor. This angle here, right?
Okay. Yeah, because that I think it was the picture that didn't miss me.
Yeah, the picture is confusing, but that is really what the diver sees, right? The diver sees the instructor way up here, and the instructor sees the diver way over here, right? And then the next one, number 5.
Yeah.
So this one is probably a very similar kind of issue, where we're going to use angles and then we're going to use distances to calculate other distances with trigonometry. So the displacement that they're talking about, the distance that the ray is displaced by the glass, is the distance between where it enters this glass and where it exits. Where it gets to all the way over here, I guess. No, the displacement is the difference between where it would have gone and where it did go. That's what they're saying. So here's the where the ray would have gone if it had not been gone through the glass. Here's where it did go when it did go through the glass. So here's the displacement we're trying to calculate, right? So the glass is 1.15 centimeters thick, first of all. And let's see here. Why is it showing two different glasses? We're only going to go through one of these, I think, right? This picture is a bad picture for this. We're actually only going to go through the first glass, so our displacement is actually from here to here. And the thickness here is 1.15. So this ends up being almost the same exact problem, except instead of figuring out the height of the person, you're figuring out how far the diver is from the edge of the tank. Does that make sense? So the light comes in here, it turns at this angle here, and it travels 1.15 centimeters downward at this angle that we calculate from Snell's law. Once you've calculated that angle from Snell's law, and you know how far it went sideways from geometry, then you can figure out where it would have gone sideways from geometry and take the difference. So let's do this in our little whiteboard here. So this is the problem we're doing. The problem with the picture that they drew is they drew two pieces of glass. We only need one piece of glass. So here's our glass, not very flat. Originally our light is coming in like this, and it would have gone straight through if the glass didn't get in the way to hit this point right here. Since the glass got in the way, it turned this way, and it hit right here. We want to know this distance, x. That's our objective, to know what that is. The angle that it turns with relative to the normal is going to be determined by Snell's law. Here's our theta 1. Here's our theta 2. We use Snell's law to get theta 2, right? Once you calculate theta 2, you will be able to calculate this distance here, which we'll call the distance d. Because once you know theta 2, you know this thickness right here is the 1.15 meters or whatever it is, right? So you know one side, you need to calculate the other side using the tangent again. Once you've calculated this distance here, you can calculate this distance because you know theta 1 is this big angle here. This is also theta 1, right? And it's the same distance, 1.15. So then you can use the tangent to calculate the total distance that it should have gone, big D, and x is just big D minus little d. And then you can calculate that distance that way. Does that make sense?
So,
Big D is calculated by taking the tangent, by using the tangent. Each one of these is done by a tangent. Little d is calculated because the tangent of, goodness, my writing is terrible right tangent of theta 2 is equal to the opposite side over the adjacent side, which is big D, or little d over 1.15, thickness of the glass. You can calculate little d from that, and the tangent of theta 1, which is the original angle of incidence, is equal to big D over 1.15. You calculate both of those distances, and then you take their difference, and you calculate, that'll be your answer.
So would it be the same for part B, column number 4 of the diagram?
Parent depth of the, yeah. Yeah.
That clears those two up pretty good. I was, the picture for number 5 was, I could
Yeah, again, this picture is not the best picture because they show it going through 2 materials when it only goes through 1. That's a bad picture again. I didn't notice that picture was a bad picture.
Can we go over 7 real quick?
Oh yes, the corner reflector. These are also called retroreflectors. This is what you use on cars or reflective things on roads and things, so that no matter what light comes in, it goes into the material, bounces around, and comes back out in the same direction. So no matter what direction you shine a light out on a reflector, you want it to shine right back at you so you see the reflector, right? And that's exactly what these are. It's called a corner reflector. And the idea is that this prism is cut so that no matter which direction you come in, this angle here and this angle over here, these angles are going to be actually, I think they end up being complements of each other. So if this one ends up here is 15 degrees, this one ends up being 75, and so on. And I think I just gave you the answer. That's good for me, right? But anyway, the other thing that you want to happen in this is you want this reflector to be, you want total internal reflection at point B and point A. So that's going to be a Brewster's angle thing. To calculate part B, you're going to use Brewster's angle equation at B and at A. So for part A, you really just need to do geometry. It's just a geometry question. So let's see. Angle of incidence at point A is 44. The angle of the first surface with the horizontal is alpha. So what they're telling you here is the equation. They're telling you this is 12 degrees. They're telling you that let's see. Yeah, so the first problem is actually just geometry because it's just reflection inside of a prism. So it's not going to turn at all. There's not going to be. It's just internal reflection. I mean, it's just normal reflection. So the reflection law says that theta incident has to equal theta reflected, right? And they've told you theta here is 44. That means that this one also has to be 44. right? If this one also has to be 44, then the angle here has to be 46. That means the angle from here up to here has to be 12 plus, let's see, 12, well, the geometry is not. I have to draw some pictures. Whenever I do geometry, I have to draw things to remember things. So let's do a picture. Oops. Yeah, that's fine, I guess. That works. So we've got this 12-degree angle here. Is that kind of what it looks like? Kind of. Cut it off at the ends. So here's our corner reflector. We have light coming in. And this angle here is 12 degrees. And then this angle, this thing coming in, this one, and going back out. This angle here, not sure I'm going to be able to do this on here just because it's too messy. That's 44. That means that this total angle from this normal down to this surface, so this angle all the way down to here has to be 46, right? That means from all the way from here, all the way up to this has to be 46 plus 12. So this angle has to be 58, right? And the one that they want is beta, which is this angle up here. This is the angle beta, right? Oh, the beta goes all the way around from here to here. So they want to know that side. So we need to figure out the angles over here, right? If this one is 44, and this one from here down to this base is 46, but this one also has to be 44. So this angle is only 2 degrees. That's useful. 44, 2 degrees. So this angle from here to here has to also be 44, but this one from here to here has to be 46. No, is that right? No, that's not right. This one has to be 44, so this one has to be 46. There we go. I got it. So this one has to be 44 as well, but from there to there has to be 46. So this is 46 right here. This angle right in here. And see, this is really messy because I'm doing it on Edu-Creations. But if we look at just that bottom one, where you have this 12-degree thing here, we just look at these bottom angles. We have this one here that's coming in, going out. This is 46 degrees. This is 44 degrees. It has to be by the reflection law. Then we have this other piece that's coming up here. And we want to know this angle up here. These two have to be going out parallel to each other. In order for them to be going out parallel and these two angles to be equal, these two angles also have to be 45. So this one has to be a 45, or 44 rather, and this one has to be a 44 in order for that to happen. Otherwise, it couldn't happen. They couldn't go out parallel that way. So this one also has to be 46, and so does this one. And for that to be 46, and this one, all of these angles have to add together. You're going to get 46 plus 44 plus 44. It's going to be geometry, something like that. I can't see it when I'm drawing it like this. I'll have to draw that one out on paper. So I can work that, but it is geometry just like this. You're just going to be doing a whole bunch of geometry. You have some things that you know. So two things that you know for sure. These two angles have to be equal, 44 and 44. They have to be. This one, this line is parallel to this line. This line intersects those two parallel lines. So the interior angles are going to be complements. This total angle is going to equal this total angle. No, it's going to equal 90 minus this total angle. So you know that much. And from that information, you can calculate. You should know this angle as well, because that one will be the same as this one, which will be 90 minus this one, and so on and so forth. So let me do it on paper, and then I'll put the paper on the overhead. I just can't do it on the computer because it's too messy. So let me draw this out really quick. Okay, I think I've got it for you. So these are the steps that you take. I'll put this on the overhead so that this won't show up on the screen if I put it on the overhead. I'm going to stop my recording at this point.